Hello, welcome back. Tonight we're going to explore something both distant and deeply personal. We're going to talk about the end of the sun, not as catastrophe or spectacle, but as a natural process, a transformation that every star like ours eventually has to face. Before we begin, go ahead and get comfortable. Settle into your space. Let the day fade into the background. This is going to be a long and easy journey through time. There's no rush at all. If you enjoy these peaceful explorations of the cosmos, you're always welcome to join us again. Feel free to subscribe. It helps these cozy journeys find more nightly travelers. We'll be here, wandering through the universe together, one calm story at a time. The sun has been shining for about 4.5 billion years. It will continue shining as much as it does now for roughly another 5 billion years. And then it will change. Not suddenly, not violently in the way massive stars explode, but gradually, beautifully, following a path written into the laws of physics. By the time this happens, Earth will be unimaginably different. Humanity, if we still exist, will have moved on long before. The changes will unfold over millions and billions of years, timescales so vast they're hard to truly grasp, but we can understand them. We can trace the sun's future with remarkable precision, following the physics of stars, the mathematics of fusion, the slow, inevitable evolution of matter and energy. So let's begin. Let's start with what the sun is right now, in this moment, and then walk slowly forward through time, watching as it transforms, ages, and eventually becomes something entirely new. The sun is a star. That seems obvious, but it's worth saying clearly. It's not unique. It's not special in the cosmic sense. It's one star among hundreds of billions in our galaxy alone. It's what astronomers call a G-type main sequence star, or a yellow dwarf, though it's not actually yellow. It appears white when seen from space. The yellow color we see from Earth's surface is due to our atmosphere scattering blue light. The sun contains about 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust, makes up the remaining tiny fraction. Its mass is about 330,000 times Earth's mass. Its diameter is about 109 times Earth's diameter. If Earth were a grape, the sun would be a sphere about 2.5 meters across. But size and mass alone don't explain what makes a star a star. What defines the sun, what makes it shine, is what's happening at its core. At the center of the sun, about 150,000 kilometers down from the surface. Conditions are extreme in ways difficult to comprehend. The temperature is around 15 million degrees Celsius. The pressure is enormous, about 250 billion times the atmospheric pressure at Earth's surface. Matter is compressed to densities about 150 times that of water. Under these conditions, hydrogen nuclei, which are simply protons, move fast enough and are pressed close enough together that they can fuse. Normally, protons repel each other. They're both positively charged, and like charges push apart. But at the sun's core, the combination of temperature and pressure overcomes this repulsion, often enough for fusion to occur. When 4 hydrogen nuclei fuse together through a series of steps, they form one helium nucleus. This process is called the proton-proton chain, and it's the primary fusion reaction powering the sun. Here's what matters. A helium nucleus has slightly less mass than the 4 hydrogen nuclei that formed it. About 0.7% of the mass is converted into energy. Following Einstein's famous equation, that tiny fraction of lost mass becomes energy, light, heat, the sunshine we feel on our faces. The sun converts about 600 million tons of hydrogen into helium every second. Of that, about 4 million tons are converted directly into energy. This has been happening continuously for 4.5 billion years, and it will continue for another 5 billion. The sun is in what astronomers call the main sequence phase of its life. This is the long, stable period when a star fuses hydrogen into helium in its core. For a star like the sun, the main sequence lasts about 10 billion years. We're roughly halfway through. During this time, the sun is in hydrostatic equilibrium. Gravity pulls inward, trying to compress the star. The pressure from fusion and heat pushes outward, resisting compression. The two forces balance perfectly. This balance is self-regulating. If the core gets slightly hotter and fusion increases, the extra pressure makes the core expand slightly, which cools it down. If the core cools slightly and fusion decreases, gravity compresses it more, heating it back up. It's remarkably stable. The sun's brightness has increased slowly over billions of years, but the day-to-day, year-to-year, even million-year-to-million-year output is extraordinarily steady. This stability is why life could develop on Earth. We've had a reliable source of light and heat for billions of years, allowing complex chemistry to evolve, ecosystems to develop, intelligence to emerge, but nothing lasts forever. Even the main sequence phase, stable as it is, gradually changes the star. As the sun fuses hydrogen into helium, the composition of the core slowly shifts. Helium is heavier than hydrogen. It sinks toward the center. Over time, the core accumulates more and more helium ash, the product of billions of years of fusion. This changes the core's properties. Helium doesn't fuse at the temperatures and pressures where hydrogen fuses. So the helium just sits there, inert, accumulating. As the hydrogen in the core depletes and helium builds up, the core contracts slightly under gravity. This contraction heats it up, which makes the hydrogen fusion in the remaining fuel happen faster. The result is that the sun slowly, very slowly, becomes brighter over time. When the sun first reached the main sequence, about 4.5 billion years ago, it was only about 70% as bright as it is today. This gradual brightening will continue. Over the next billion years, the sun's luminosity will increase by about 10%. That might not sound like much, but it has profound consequences for Earth. In about 1 billion years, the sun will be about 10% brighter than it is now. This increased heat will alter Earth's climate in fundamental ways. The oceans will begin to evaporate more rapidly. More water vapor in the atmosphere will create a stronger greenhouse effect, which traps more heat, which causes more evaporation. It's a runaway process. Eventually, over hundreds of millions of years, Earth's oceans will evaporate completely. Water vapor will rise high into the atmosphere, where ultraviolet light from the sun will break it apart. Hydrogen, being light, will escape into space. Oxygen will react with rocks on the surface. Earth will become a hot, dry world More like Venus is today. Life as we know it will not survive this. Complex life will likely disappear much earlier, perhaps in a few 100 million years. As temperatures rise and oceans acidify from increased evaporation and atmospheric changes, simple microbial life might persist longer in protected environments. But eventually even that will fade. This is not immediate, not something to worry about in human terms, but it's worth understanding that the sun's gradual brightening presents a challenge long before the red giant phase begins. If humanity still exists in 1 billion years, which is difficult to even imagine, we will have had to move elsewhere or find ways to manage Earth's climate on a planetary scale. But the universe is vast. There will be other places, other possibilities. After the sun has spent about 10 billion years on the main sequence, the hydrogen in the core will be nearly exhausted. The core, now mostly helium, will contract under gravity. There's no fusion happening there because helium requires higher temperatures to fuse than the core can provide yet. But as the core contracts, it heats up from the compression. This heat radiates outward to a shell of hydrogen surrounding the core. In that shell, hydrogen fusion continues, actually becoming more vigorous than it ever was in the core. This shell fusion releases energy that pushes the sun's outer layers outward. The star begins to expand. At the same time, even though the outer layers are expanding and cooling, the total energy output of the sun increases dramatically because the surface area is growing. The sun enters the red giant phase. Over about 1 billion years, the sun will swell enormously. Its outer layers will extend past the orbit of Mercury, possibly past Venus, perhaps even reaching Earth's current orbit. The surface temperature will drop from about 5,500 degrees Celsius to around 3,000 degrees. Cooler stars appear redder, which is why this phase is called a red giant. But even though the surface is cooler, the sun will be hundreds of times more luminous than it is today because it will be so much larger. A bigger surface area radiates more total energy, even if each square meter radiates less. What happens to the planets during this expansion? Mercury, the closest planet, will almost certainly be engulfed. The sun's outer layers will reach beyond Mercury's orbit, and the planet will spiral inward through friction with the thin outer atmosphere of the red giant sun. Eventually, Mercury will vaporize, its atoms mixing with the sun's outer layers. Venus will likely meet the same fate. The expanding sun will probably engulf it, and Venus too will spiral inward and be destroyed. Earth's fate is less certain, and this uncertainty is important to acknowledge honestly. Some models suggest Earth will be engulfed. Others suggest it will survive barely, just outside the sun's extended atmosphere. Here's why it's uncertain. As the sun becomes a red giant, it will lose mass. The outer layers are only weakly bound to the core, and a significant fraction will drift away into space over time. As the sun loses mass, its gravitational pull on the planets weakens slightly. The planet's orbits expand outward a bit. Whether Earth's orbit expands enough to avoid being engulfed depends on the details of how fast the sun expands versus how fast it loses mass. And these details are still being refined in models. If Earth is engulfed, it will spiral inward through the sun's outer atmosphere. The friction will heat it, vaporize its surface, and eventually the planet will be destroyed completely. If Earth avoids engulfment, it will still be utterly transformed. It will be a scorched, airless rock orbiting just outside a vast red star. Any atmosphere will have been stripped away. Any water will be long gone. The surface will be molten from the intense heat. Either way, Earth as we know it will not survive the red giant phase. But remember, this is 5 billion years away. To put that in perspective, 5 billion years ago, Earth had just formed. Life hadn't begun yet. The entire history of life on Earth, from the first microbes to now, fits comfortably within the time we have. Before the sun begins this transformation, let's return to the sun itself and follow what happens at the core. The core continues contracting as the hydrogen shell burns around it. Contraction releases gravitational energy, which heats the core. Eventually, after perhaps 1 billion years of being a red giant, the core temperature reaches about 100 million degrees Celsius. At this temperature, helium can fuse. 3 helium nuclei can fuse together to form carbon through a process called the triple alpha process. Some carbon can fuse with more helium to form oxygen, but the moment when helium fusion ignites is dramatic. At least by stellar standards, in a star like the Sun, the core at this point is degenerate. This is a quantum mechanical state where matter is so dense that the electrons are packed as tightly as physics allows. In degenerate matter, pressure doesn't depend much on temperature. This creates an instability. When helium fusion starts, it releases energy and heats the core. And in normal gas, heating causes expansion, which cools things back down. But in degenerate matter, the pressure doesn't increase much with temperature, so the core doesn't expand right away. The temperature rises. Fusion accelerates. Temperature rises more. Fusion accelerates more. It's a runaway process called the helium flash. For a few seconds, the core produces as much energy as the entire galaxy. But this energy goes into heating the core, lifting it out of the degenerate state, and causing it to expand. The expansion cools the core. Fusion rates drop, and the star stabilizes. From the outside, you wouldn't see much. The helium flash happens deep in the core, and the outer layers absorb the energy. The sun doesn't explode or even brighten noticeably, but internally the structure changes. Now the sun has a helium-fusing core surrounded by a hydrogen-fusing shell, surrounded by the vast extended envelope of the red giant. The sun will spend about 100 million years fusing helium into carbon and oxygen in its core. This is much shorter than the main sequence phase, but it's still a substantial amount of time. During this period, the sun will shrink slightly and become less luminous than it was at the peak of the red giant phase, though it will still be much larger and brighter than it is today. But eventually, the helium in the core will be exhausted. The core, now carbon and oxygen, will contract again. For the sun, this is as far as fusion goes. The core will never get hot enough to fuse carbon. That requires temperatures and pressures only found in more massive stars. So the core contracts and heats, but doesn't ignite new fusion. Instead, it becomes a hot, dense, inert ball of carbon and oxygen. Meanwhile, fusion continues in shells around the core. First a helium fusing shell, then outside that a hydrogen fusing shell. These shells are unstable. They pulse. Sometimes the helium shell burns vigorously, producing so much energy that it briefly pushes the hydrogen shell outward and shuts it off. Then things settle down and both shells burn again. These thermal pulses happen every few tens of thousands of years. Each pulse ejects some of the sun's outer layers into space. The sun begins to lose mass more rapidly. Over a few 100,000 years, the thermal pulses and stellar winds blow away the sun's entire outer envelope. The mass loss accelerates. The outer layers, barely bound to the core by gravity, drift outward into space. These expelled layers form an expanding shell of gas around the dying star. Ultraviolet light from the hot exposed core ionizes the gas, making it glow. This glowing shell is called a planetary nebula. The name is historical and misleading. It has nothing to do with planets. Early astronomers using small telescopes thought these objects looked round and planet-like, so the name stuck. But planetary nebulae are among the most beautiful objects in the night sky. The gas forms intricate shapes, shells, rings, sometimes bipolar lobes extending in opposite directions. Colors vary depending on which elements are glowing. Oxygen produces green and blue-green light. Hydrogen produces red. Nitrogen produces red and orange. Sulfur produces red. The shapes are influenced by magnetic fields, by rotation, by binary companion stars if they exist, by the geometry of how the mass was lost. Each planetary nebula is unique. They're cosmic art, created by the natural death of a star. The gas expands outward at speeds of tens of kilometers per second. Over tens of thousands of years, the nebula grows and fades, eventually mixing with the interstellar medium and dispersing at the center of the planetary nebula. The exposed core of the sun remains. This core is incredibly hot, perhaps 100,000 degrees Celsius at the surface. It's also incredibly dense, about the size of Earth, but with about half the sun's current mass. It's no longer fusing anything. There's no more fuel. The core is made of carbon and oxygen, and it's not hot enough to fuse those elements, but it's still radiating energy, glowing from stored heat. It's a white dwarf. A white dwarf is supported against gravity, not by fusion or gas pressure, but by electron degeneracy pressure. The same quantum mechanical effect that was present in the core before the helium flash. Electrons cannot be compressed beyond a certain point. They resist, not because of any force in the classical sense, but because of the Pauli exclusion principle, a fundamental rule of quantum mechanics. This support can hold up a white dwarf indefinitely, as long as the mass isn't too high. There's a limit called the Chandrasekhar limit at about 1.4 solar masses. Beyond that, electron degeneracy pressure isn't enough, and the star would collapse further. But the sun's white dwarf will be comfortably below that limit, around 0.5 to 0.6 solar masses. The rest of the sun's mass was lost during the red giant and planetary nebula phases. The white dwarf will be stable. It will sit there, radiating its stored heat into space, slowly cooling over billions of years. What does the solar system look like now? Mercury and Venus are gone, consumed, or vaporized during the red giant phase. Earth, if it survived, is a dead, scorched world orbiting the white dwarf. No atmosphere, no water, just a ball of rock and metal. Mars, farther out, was also baked during the red giant phase. Though it may have retained more of its structure than Earth, any ice it had is long gone. The asteroid belt between Mars and Jupiter has survived mostly intact, though some asteroids may have been perturbed or vaporized by the expanded Sun. Jupiter and the outer planets, Saturn, Uranus, Neptune, are still there. They're far enough that they weren't engulfed, though they experienced dramatic changes. During the red giant phase, Jupiter and Saturn received much more light and heat than they do now. Their atmospheres were heated. Any icy moons may have experienced brief periods where liquid water existed on their surfaces. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy shell today. During the red giant phase, that ice may have melted, creating a temporary world with surface oceans. But once the Sun became a white dwarf, the heat dropped dramatically. The outer solar system became cold again. Colder, actually, than it is now, because the white dwarf emits far less total energy than the main sequence Sun. Europa would freeze solid again. Any temporary flourishing of chemistry or even life would end. The outer solar system becomes a frozen, dark realm lit only by the faint glow of the white dwarf. The white dwarf will cool slowly, very slowly. At first, when newly exposed, it's extremely hot, over 100,000 degrees. It radiates mostly an ultraviolet light, invisible to human eyes but energetic. Over millions of years, it cools to tens of thousands of degrees, appearing blue-white. After tens of millions of years, it cools to around 10,000 degrees, appearing white. After hundreds of millions of years, it might cool to around 5,000 degrees, similar to the Sun's current surface temperature, appearing yellowish. After billions of years, it cools to a few thousand degrees, appearing red. Eventually, after tens of billions of years, longer than the current age of the universe, it would cool to the point where it no longer emits visible light. It would become a black dwarf, a cold, dark sphere of degenerate matter drifting through space. No black dwarfs exist yet in the universe. The universe isn't old enough. Even the oldest white dwarfs are still glowing faintly, but given enough time, all white dwarfs will eventually become black dwarfs. As the white dwarf cools, the solar system remains stable in one sense but dynamic in another. The planets continue orbiting. The white dwarf's gravity holds them in place just as the Sun's gravity does now, though the orbits may have shifted during the mass loss phases. But over extremely long timescales, orbital dynamics become chaotic. Small gravitational perturbations accumulate. Planets interact with each other, tugging slightly on each other's orbits. Over billions or tens of billions of years, these small effects can add up. Orbits can shift. Eccentricities can grow. Eventually, some planets might be ejected from the solar system entirely, flung out into interstellar space by gravitational interactions. Others might spiral inward and collide with the white dwarf, briefly heating its surface as their material accretes onto it. The solar system, over enough time, will gradually dissipate. The white dwarf may end up alone, or with only one or two remaining planets, the rest scattered into the galaxy. Let's zoom out even further and think about what happens on truly cosmic timescales. The white dwarf continues cooling. It's now a black dwarf, cold and dark, invisible except for its gravitational influence. it will remain stable for an almost incomprehensible amount of time. White dwarfs don't decay in any normal sense. They're not radioactive. They're just cooling, and eventually there's nothing left to cool from. But on timescales of perhaps 10 to the 32 years, far longer than the current age of the universe, even atoms may not be stable. Some theories predict proton decay, where protons very slowly, very rarely, break down into lighter particles and energy. If this happens, the carbon and oxygen nuclei in the black dwarf would gradually disappear. The timescale is so long it's almost meaningless. 10 to the 32 years is a 1 followed by 32 zeros. The current age of the universe is less than 10 to the 10th years. But given enough time, if proton decay occurs, the black dwarf would slowly evaporate into radiation and lighter particles, eventually disappearing completely. If protons don't decay, then the black dwarf would remain indefinitely, a cold, dark sphere drifting through an increasingly empty, dark, and cold universe. Let's return now to something more immediate. Not immediate in human terms, but in cosmic terms. The transformation of the sun from main sequence star to red giant to white dwarf will take about 7 to 8 billion years total from now. During that time, the universe will continue evolving. Galaxies will continue colliding and merging. Our Milky Way will collide with the Andromeda Galaxy in about 4 billion years before the sun becomes a red giant. The collision will scramble the orbits of stars, but the sun and solar system will likely survive intact, just in a different location within the merged galaxy. Stars will continue forming in gas clouds, living their lives and dying. The universe will produce new generations of stars, some with planetary systems, some with planets that might harbor life. The processes that created Earth and eventually led to us will repeat countless times in countless places. The sun is not unique. Its death is not special. It's part of a natural cycle that has been happening throughout cosmic history and will continue far into the future. There's a poetic symmetry to stellar evolution. Stars are born from clouds of gas and dust, pulled together by gravity. They spend most of their lives in a stable state, fusing hydrogen. Then they swell, shed their outer layers, and leave behind a dense core. That core cools and fades. The gas they shed enriches space with heavier elements. Those heavier elements mix with the interstellar medium. New clouds form. New stars are born, now with small amounts of carbon, oxygen, iron, and other elements that weren't present in the first generation of stars. Planets can form from these enriched clouds. Rocky planets with solid surfaces. Planets with water and atmospheres. Planets where complex chemistry can occur. We are part of this cycle. The atoms in our bodies were forged in stars that lived and died before the sun formed. Carbon in our DNA, oxygen in the water we drink, calcium in our bones, iron in our blood. All created in stellar cores and scattered by stellar deaths. When the sun becomes a white dwarf, it will have added its contribution to the cosmic recycling program. The carbon and oxygen it created, now locked in the white dwarf, will eventually be incorporated into future stars if the white dwarf is ever disrupted. More immediately, the elements created during the sun's red giant phase and scattered in the planetary nebula will enrich nearby gas clouds, perhaps contributing to future star formation. The sun's death will be part of the universe's ongoing process of creation and transformation. As this journey comes to a close, let's think about what this all means. The sun will die. That's inevitable. But death in a stellar context isn't an ending in the way we usually think of endings. It's a transformation. The sun won't disappear. It will change form. From a main sequence star to a red giant to a planetary nebula to a white dwarf. Matter and energy rearranged, following the laws of physics. And the timeline is so vast that it's almost comforting. 5 billion years before the sun begins to swell. Billions more years of transformation. Timescales so long that they dwarf all of human history, all of biological history, all of Earth's geological history. Whatever happens to humanity, we will not witness the sun's death. We'll be long gone, one way or another, either extinct or evolved into something unrecognizable or scattered among the stars. The sun's end is not our end. It's just one chapter in the ongoing story of matter and energy in the universe. And there's beauty in understanding this, in knowing that the sun, for all its importance to us, is subject to the same natural processes as every other star, that its fate is written in physics, predictable, understandable. We can trace the future with remarkable clarity. We can say with confidence what will happen, even though it's billions of years away. That's the power of science, to understand, to predict, to see patterns in nature and follow them forward or backward through time. The sun is shining tonight as it has for billions of years, as it will for billions more. It's fusing hydrogen into helium, converting mass into energy, holding itself up against gravity through the pressure of fusion. It's in the middle of its life, stable and steady, providing the light and warmth that makes life on Earth possible. That will continue. Tomorrow the sun will rise, a year from now, 1,000 years from now, 1,000,000 years from now. The changes are slow, gradual, playing out over timescales we can barely comprehend. But eventually, far in the future, the sun will transform. It will swell into a red giant, beautiful and vast. It will shed its outer layers in a glowing nebula. It will leave behind a white dwarf that will slowly cool over ages. And the universe will continue. Stars will keep forming and dying. Galaxies will keep evolving. The cosmic story will go on. We're privileged to be here now in this moment, able to understand it, able to look up at the sun and know what it is, how it works, where it came from, where it's going. That understanding is a gift, a product of centuries of observation, thought, and discovery. And tonight, as you drift towards sleep, you can rest easy knowing that the sun will be there tomorrow, that the processes keeping it shining are stable and well understood, that the universe, for all its eventual changes, follows orderly laws we've learned to comprehend. So let it all settle now, the red giants and white dwarfs, the timescales of billions of years, the transformation of stars and the recycling of elements. Let your breathing slow. Feel the comfort of the present moment. You're here, safe, on a planet orbiting a stable star in the prime of its life. The sun will rise tomorrow, as it always has, and it will continue rising for billions of years to come. There's time, so much time. For now, just rest. Close your eyes, let your body relax completely. The universe is vast and ancient and will continue long after we're gone. But right now, in this moment, everything is calm. Sleep well. The stars will keep shining. The cosmos will keep turning. And tomorrow, if you wish, there will be new things to explore, new questions to wonder about. But tonight, just rest. Good night.